Introduction to RFC 6698 DANE TLSA. Welcome to the channel. Please consider subscribing. I produce videos daily covering a wide variety of cloud topics with focus on networking. Also, hit the bell icon to get notified of new videos. Today we are diving deep into RFC 6698, which defines the DNS-Based Authentication of Named Entities Protocol, commonly known as DANE, and specifically its Transport Layer Security Authentication Record Type called TLSA. This is an Internet Standards Track document published in August 2012 by Paul Hoffman from the VPN Consortium and Jakob Schleider from Kire AB. The fundamental problem that data authentication of named entities transport layer security authentication addresses is a critical vulnerability in how we secure Internet communications today. When you connect to a website using TLS, the security of that encrypted connection depends entirely on trusting third-party certificate authorities. These certificate authorities are organizations that vouch for the authenticity of the certificates used by web servers and other TLS-enabled services. The issue is that the current public certificate authority model is fundamentally vulnerable because it allows any of the hundreds of trusted certificate authorities to issue a certificate for any domain name in the world. If even a single certificate authority is compromised, whether through a security breach, voluntary betrayal, or government coercion, that compromised certificate authority can issue fraudulent certificates for any website. This means an attacker with a fake certificate could intercept and decrypt your encrypted communications without you ever knowing. Data authentication of named entities transport layer security authentication provides an elegant solution to this problem by leveraging the domain name system infrastructure, secured by domain name system security extensions, to allow domain administrators to explicitly specify which certificates or public keys are authorized for their transport layer security servers. This shifts the trust model from relying on any of hundreds of certificate authorities to trusting the domain name system hierarchy itself, where each domain can only vouch for itself and its subdomains. DANE TLSA Solution Overview. Now let us explore how DANE TLSA solves the trust problem I just described. The key insight behind DANE is that the entity responsible for managing DNS records for a domain should also be able to specify which TLS certificates are valid for that domain. After all, if you trust DNS to tell you where to connect, why not also trust it to tell you what certificate to expect? DANE uses a new DNS record type called TLSA, which stands for Transport Layer Security Authentication. This record associates a TLS server certificate or public key with the domain name where the record is published. The TLSA record is secured using DNSSEC, which provides cryptographic proof that the record has not been tampered with and genuinely comes from the domain owner. The architecture diagram shows how domain name authentication of named entities transport layer security authentication works in practice. When a client wants to connect to a server, it first performs a domain name system lookup for the transport layer security authentication record associated with that service. The client receives the transport layer security authentication record, which has been signed using domain name system security extensions all the way up to the domain name system root. The client then validates the domain name system security extension signatures to ensure the record is authentic. When the transport layer security connection is established, the client receives the server's certificate. The client then compares the certificate it received against the information in the validated transport layer security authentication record. If they match, the connection proceeds. If they do not match, the connection is aborted because the certificate is not authorized by the domain owner. This approach provides a crucial security improvement. Unlike the public certificate authority model where any certificate authority can issue certificates for any domain, with DANE only the entity that controls the DNS for a domain can publish TLSA records for that domain. A compromised certificate authority in another part of the world cannot affect your domain because they cannot modify your DNS records. The security of DANE relies on DNSSEC, which uses a hierarchical trust model where each zone can only sign records for its own subdomains. This implements the security principle of least privilege that is lacking in the public certificate authority model. Certificate usage types. The certificate usage field is perhaps the most important part of a TLSA record because it fundamentally changes how the TLS certificate is validated. There are 4 defined usage types, each serving different use cases and providing different security properties. Certificate usage 0 is called CA constraint or PKIX-TA. When you use this value, you're specifying a CA certificate that must be present somewhere in the PKIX certification path for the server's certificate. The server's certificate still must pass normal PKIX validation, meaning it must chain to a trusted root CA. However, additionally, one of the CA certificates in that chain must match the TLSA record. This allows a domain owner to restrict which CS can issue valid certificates for their domain while still requiring traditional PKIX validation. Certificate usage 1 is called Service Certificate Constraint or PKIX-EE. This usage specifies the exact end entity certificate that the server must present. Like usage 0, the certificate must also pass PKIX validation. This gives the domain owner complete control over exactly which certificate is valid for their service, but still requires that certificate to be issued by a trusted CA. Certificate usage 2 is called Trust Anchor Assertion or DANE-TA. This is more powerful because it allows the domain owner to specify their own trust anchor that does not need to be in the client's pre-configured list of trusted certificate authorities. The certificate must still pass PKIX path validation, but the matching certificate from the TLSA record is used as the trust anchor for that validation. This allows organizations to run their own certificate authority for their domains without relying on public certificate authorities. Certificate usage 3 is called Domain Issued Certificate or DANE-EE. This is the most autonomous option because it completely bypasses PKIX validation. The server certificate simply must match the TLSA record directly. The certificate does not need to be signed by any certificate authority at all, allowing for fully self-signed certificates that clients will accept based solely on the TLSA record. This enables domains to be completely independent of the certificate authority system. TLSA record domain name format. The TLSA record is not stored directly at the domain name of the TLS server. Instead, it uses a prefixed domain name format that includes the port number and transport protocol. This allows different TLSA records for different services running on the same host. The domain name for a TLSA record is constructed by prepending 2 labels to the base domain name. The first label, which becomes the leftmost part of the name, is an underscore followed by the decimal port number with no leading zeros. For example, for HTTPS on port 443, this would be underscore 443. The second label is an underscore followed by the transport protocol name. The defined transport names are TCP, UDP, and SCTP. For most TLS applications, this will be underscore TCP. These 2 labels are then prepended to the fully qualified domain name of the TLS server. So for an HTTPS server running on www.example.com, the complete TLSA record name would be underscore 443._tcp.www.example.com. For an SMTP server using START-TLS on port 25 at mail.example.com, it would be underscore 25._tcp.mail.example.com. This naming convention is important because it allows fine-grained control over certificate associations. You can have different certificates for different ports on the same host, and you can have different certificates for different protocols. The TLSA record applies only to the specific port number and transport specified in its name. The diagram shows several examples of this naming convention. You can see how the port number and protocol combine with the base domain name to form the complete TLSA record location. When a TLS client wants to validate a connection, it constructs this prefixed name based on where it is connecting and looks up the TLSA record at that specific location. DNSSEC dependency and validation. A critical aspect of DANE TLSA that cannot be overstated is its complete dependency on DNSSEC for security. Without DNSSEC, DANE provides no security benefit whatsoever. Let me explain why this is the case and how the validation process works. If TLSA records were not protected by DNSSEC, an attacker who could perform a man-in-the-middle attack on your network could simply forge both the TLS certificate and the TLSA record. They would return their own malicious TLSA record that matches their fake certificate, and the client would accept the connection. DNSSEC prevents this by cryptographically signing the TLSA record all the way up the DNS hierarchy to the root. The RFC defines specific requirements for how TLSA records must be validated. If a TLSA record set has a DNSSEC validation state of secure, meaning all signatures from the record up to a trust anchor have been verified, then the client must use those records for certificate validation. If the validation state is bogus, meaning the signatures are invalid or fail to verify, the client must abort the TLS connection or refuse to start one. If the validation state is indeterminate or insecure, meaning the domain does not use DNSSEC or there is no way to validate the signatures, then the TLSA records cannot be used and the client must fall back to traditional certificate validation. The diagram illustrates the DNSSEC validation chain that must be verified. The TLSA record is signed by the zone key for the domain. That zone key is authenticated by a DS record in the parent zone, which is signed by the parent zone key. This chain continues up through the CUM zone, or whatever top-level domain applies, until it reaches the DNS root. The client must have the root zone's key as a trust anchor and must verify every signature in this chain before the TLSA record can be trusted. Clients can perform this validation themselves, or they can rely on a trusted DNSSEC validating resolver that communicates over a secure channel. TLS client processing flow. Now let us walk through exactly how a TLS client should process TLSA records when establishing a connection. Understanding this flow is essential for implementing or troubleshooting DANE TLSA. The process begins when the client wants to establish a TLS connection to a specific host, port, and protocol. The client first constructs the TLSA domain name using the prefixed format we discussed earlier, combining the port number, protocol, and host name. The client then performs a DNS lookup for TLSA records at that domain name. This lookup must return not only the TLSA records but also their DNSEC validation status. If the DNSEC validation state is bogus, the client must immediately abort and not attempt the TLS connection. If the state is indeterminate or insecure, the client cannot use the TLSA records and must fall back to normal PKI-X validation without DANE. Assuming the DNSSEC validation state is secure, the client examines each TLSA record in the response. Records with unknown certificate usages, selectors, or matching types must be considered unusable and ignored. Records with malformed data or cryptographic algorithms the client considers too weak must also be ignored. If no usable TLSA records remain after this filtering, the client falls back to normal validation. With one or more usable TLSA records in hand, the client proceeds with the TLS handshake. When it receives the server's certificate and potentially a certificate chain, it attempts to match each TLSA record against the certificate according to the rules for that record's certificate usage, selector, and matching type. If any TLSA record successfully matches, the certificate is accepted. If all TLSA records are checked and none match, the client must abort the TLS handshake. The client should not fall back to traditional validation in this case because the presence of TLSA records indicates the domain owner's intent to use DANE, and failing to honor that intent would allow an attacker to bypass the protection. Mandatory to implement features. Request for Comments 6698 specifies certain features that all conforming TLS clients must implement to ensure interoperability. These mandatory requirements establish a baseline that allows domain authentication of named entities TLSA to function consistently across different implementations. For certificate usages, clients must be able to correctly interpret all four defined values 0, 1, 2, and 3. This means every client must understand how to handle certificate authority constraints, service certificate constraints, trust anchor assertions, and domain-issued certificates. A client cannot claim DANE support if it only implements some of these usages. For selectors, clients must support both selector type 0, which is the full certificate, and selector type 1, which is the subject public key info. This ensures that domain administrators have flexibility in choosing how to specify their certificate associations without worrying about client compatibility. For matching types, clients must support matching type 0, which is the exact match with no hash, and matching type 1, which uses SHA-256 hashing. Support for matching type 2, which uses SHA-512 hashing, is recommended but not strictly required. The SHA-256 requirement ensures that the most common and efficient configuration will work universally. These mandatory features reflect a balance between ensuring broad interoperability and allowing for future extensibility. By requiring support for all certificate usages but making the stronger SHA-512 hash optional, the specification ensures that basic DANE TLSA will work everywhere while allowing security-conscious deployments to use stronger algorithms where supported. Comparing DANE to Public Certificate Authorities risk analysis. Let me provide a detailed comparison of the security properties of DANE versus the traditional public CA model. Understanding these differences helps you evaluate which model is more appropriate for different scenarios. When comparing key compromise risk, DNSSEC keys vary significantly in their protection levels. The DNS root key has protections comparable to or exceeding those of major certificate authorities, with multiple physical security measures and ceremony procedures. However, individual domain keys might receive much less protection. In contrast, public certificate authorities generally employ security experts and protect their keys carefully due to financial incentives and client requirements, though highly publicized compromises have occurred. The number of keys that could compromise a given domain is very different between the two models. With DANE TLSA, only the keys in the DNS chain from your domain up to the root can affect your TLSA records. Typically this is about 6 keys, half of which are key signing keys that can be stored offline. With public certificate authorities, any of the 100+ trusted root certificate authorities can issue a certificate for any domain. The impact of compromise also differs significantly. If a DNSKEY for example.com is compromised, only example.com and its subdomains are affected. Even compromising the .com zone key would only affect .com domains. Only the DNS root key compromise would have equivalent impact to an unconstrained public CA compromise. But with public CAs, compromising even one CA allows attacks against any domain in the world. This analysis shows that DANE provides much better containment of compromise impact, even if individual keys might not always be as well protected as certificate authority keys. DNS caching considerations. Proper handling of DNS caching is essential for DANE TLSA security. Implementations that cache TLSA records incorrectly can be vulnerable to attacks or can experience service disruptions during legitimate certificate changes. The RFC emphasizes that implementations should rely on their DNS resolver for confirmation of certificate associations rather than maintaining their own long-term caches. Many platforms already cache DNS lookups appropriately, and implementations should leverage these existing caching mechanisms rather than implementing additional caching layers. When caching is used for performance, implementations must strictly observe the time to live information reported by DNS. The TTL indicates how long a record can be considered valid. Ignoring TTL values can lead to two serious problems. First, if an attacker previously served a malicious TLSA record and you cache it beyond its intended lifetime, you remain vulnerable even after the legitimate record is restored. Second, if a domain administrator changes their certificate and updates their TLSA record, clients with stale cached records will reject the new valid certificate. The diagram illustrates the correct caching behavior. When a client receives a TLSA record, it stores the record along with its TTL. Before the TTL expires, the cached record can be used. Once the TTL expires, the client must re-query DNS to get fresh data. This ensures that clients track legitimate changes while still benefiting from caching performance. Administrators performing certificate rollovers should consider TTL values when planning their transition timeline, ensuring old records have expired before removing the old certificate from the server. Certificate rollover procedures. Certificate rollover is a routine operational task that must be handled carefully when DANE TLSA is in use. The RFC describes a procedure similar to the pre-publish method used for DNSSEC key rollovers, and following this procedure is essential to avoid service disruptions. The rollover process begins with your current state, a single TLSA record matching your current certificate. When you are ready to begin the rollover, you first generate or obtain the new certificate that will be used after the transition. You then generate the corresponding TLSA record for this new certificate. The critical step is adding the new TLSA record alongside the existing one before making any changes to the TLS server. Both records should be published in DNS simultaneously. This ensures that clients caching the old record will still match the old certificate, while clients fetching fresh records will see both options. After the new records have propagated to all authoritative nameservers, you must wait for the TTL of the old record to expire. This ensures that no clients anywhere are still caching only the old record. Only after this waiting period should you switch the TLS server to use the new certificate. Once the server is using the new certificate and enough time has passed for all clients to have refreshed their cached TLSA records, you can safely remove the old TLSA record. This completes the rollover. The diagram shows this timeline visually, emphasizing the critical waiting period where both records must be published. Skipping this waiting period can cause clients with cached old records to reject the new certificate. Using TLSA with DNAME records. DNAME records provide a different aliasing mechanism that can be useful for TLSA deployment in certain scenarios. While CNAME creates an alias for a single name, DNAME creates an alias for an entire subtree of names. This has interesting implications for TLSA records. When you use a DNAME record, all names below the DNAME owner name are aliased to corresponding names below the DNAME target. This allows wholesale aliasing of prefixed records like TLSA, SRV, and others without requiring individual CNAME records for each one. However, DNAME has an important limitation. It can only alias subtrees, not the apex name itself. This means if you have a DNAME at _tcp.sub5.example.com pointing to _tcp.sub6.example.com, then _443._tcp.sub5.example.com will be aliased to _443._tcp.sub6.example.com. But you would still need a separate CNAME for sub5.example.com itself to point to sub6.example.com. The practical use case for DNAME with TLSA is when you want to delegate all TLS certificate management for a host name to another domain. By creating a DNAME for the _TCP subdomain, all port-specific TLSA records automatically follow the alias. This is cleaner than creating individual CNAMEs for each port. The slide shows an example zone configuration using DNAME. The hostname sub5.example.com is aliased to sub6.example.com using CNAME. The underscore TCP subtree under sub 5 is aliased to the underscore TCP subtree under sub 6 using dname. The actual TLSA record is published only in the sub 6 zone and automatically applies to both names through the dname alias. Selector type selection guidelines. Choosing between Selector 0 for full certificate and Selector 1 for subject public key info involves trade-offs that depend on your operational requirements and security preferences. Let me explain the considerations for each choice. Selector 0, matching the full certificate, provides the most precise specification. Every field of the certificate is captured, including validity dates, extensions, issuer information, and the signature. This means any change to the certificate requires updating the TLSA record, even if the key stays the same. The advantage is that you have complete control over exactly which certificate is accepted. The disadvantage is less operational flexibility. Selector 1, matching the subject public key info, is more flexible, because it only captures the public key and algorithm. You can renew or reissue certificates with the same key without updating TLSA records. This is particularly valuable for certificate usage 3 where you control the certificate entirely. However, you must trust that any certificate issued with that key is acceptable. There is a subtle security consideration with Selector 1 for certificate authorities certificates when using usage 0 or 2. Certificate authorities sometimes reissue their certificates with different signature algorithms or validity periods while keeping the same key. With Selector 1, any of these reissued certificates would match. You must trust that the certificate authority will not misuse this flexibility. The decision flowchart on the slide guides you through the selection process. If you need precise certificate pinning and can manage frequent TLSA updates, use Selector 0. If you want certificates to survive renewal and trust the key holder, use Selector 1. For most deployments using usage 3 with self-managed certificates, Selector 1 with SHA-256 matching provides the best balance. Wildcard TLSA records. Wildcards in DNS are a powerful feature that can simplify administration, and they can be used with TLSA records in limited but useful ways. However, the way wildcards work with TLSA records requires careful understanding because of the prefixed naming structure. With TLSA records, you cannot simply create a wildcard at the base domain level and have it applied to all TLSA lookups. This is because TLSA lookups include the port and protocol prefix. A wildcard must be placed at a layer below the host name in the TLSA naming hierarchy. The most practical use of wildcards with TLSA is when you want the same certificate to be valid for all TCP ports on a given host. You can create a wildcard record at the _TCP subdomain level. For example, a record at *_TCP.www.example.com would match queries for _443._TCP.www.example.com, _25._TCP.www.example.com, and any other port. This can be useful in scenarios where the same certificate and key are used for all services on a host. Instead of creating individual TLSA records for each port, a single wildcard record covers them all. This reduces administrative overhead and ensures consistency. It is important to note that a wildcard in a certificate's subject alternative name or common name is completely unrelated to DNS wildcards for TLSA lookups. A certificate with a wildcard name like star.example.com does not require or imply any special TLSA record format. The TLSA lookup is always for the specific fully qualified domain name being connected to. Securing the last hop. For DANE TLSA to provide security, the application must know with certainty whether the TLSA records it read or DNSSEC validated or not. This section of the RFC discusses how to achieve this last hop security between the application and DNS validation. There are several approaches an application can use. The first is to have its own DNS resolver and DNSSEC validation stack built into the application itself. This provides the highest assurance because the application directly verifies all cryptographic signatures. However, this adds significant complexity to application development. The second approach is to communicate through a trusted channel to a local domain name system resolver that performs domain name system SEC validation. This could be a resolver running on the same machine as the application, with communication happening through a secure local mechanism like a Unix domain socket. The application trusts the operating system to provide accurate validation status. The third approach is to communicate over a secured channel to a remote DNS resolver that performs validation. This could use DNS over TLS, DNS over HTTPS, IPsec, TSIG, or SIG0 to protect the communication. The application must authenticate the resolver and trust it to perform validation correctly. The fourth approach extends the third by having the remote resolver itself obtain validated responses from yet another resolver over a secure channel. This creates a chain of trust that must be secure at every link. The diagram illustrates these different approaches and their relative security properties. Each has trade-offs between implementation complexity, performance, and security assurance. Related RFCs and extensions. RFC 6698 established the foundation for DANE TLSA, but several subsequent RFCs have extended and refined the protocol for specific use cases and operational improvements. Understanding this ecosystem of related standards helps you deploy DANE effectively. RFC 6394 is actually a predecessor document that defined the use cases and requirements for DANE. It was published before RFC 6698 and provides valuable context for understanding why DANE was designed the way it was. If you want to understand the rationale behind design decisions, RFC 6394 is essential reading. RFC 7218 adds acronyms to simplify discussions about DANE. It defines the short names PKIX-TA, PKIX-EE, DANE-TA, and DANE-EE for certificate usages 0, 1, 2, and 3 respectively. These names are more memorable than numbers and are now commonly used in documentation and discussion. RFC 7671 provides updates and operational guidance based on implementation experience after RFC 6698 was published. It clarifies ambiguities, provides deployment recommendations, and updates some requirements. For example, it recommends that applications support only DANE-EE and DANE-TA, meaning usages 3 and 2, rather than all 4 usages. This is because the PKIX usages add complexity without providing additional security in most scenarios. RFC 7672 specifies how to use DANE with SMTP for email security. Email is one of the most important applications of DANE because it enables authenticated encryption for mail transfer between servers without requiring pre-shared certificates. RFC 7673 extends DANE to work with SRV records, which are used by many application protocols to discover service endpoints. This is important because the original DANE specification did not cover the indirection that SRV records introduce. DANE with SRV records RFC 7673 overview. Many application protocols use DNS-SRV records to discover service endpoints rather than connecting directly to a host name. For example, XMPP for instant messaging, SIP for voice communication, and various other protocols. RFC 7673 extends DANE to work with these SRV-based services. The challenge with SRV records is that they introduce a level of indirection. When you want to connect to an XMPP server for example.com, you do not connect to example.com directly. Instead, you look up the SRV record _xmpp-client._tcp.example.com, which tells you to connect to something like xmpp1.hosting.example.net on port 5222. The question becomes, where should the TLSA record be published? Should it be at the service domain, for example, example.com, or at the target server hostname, xmpp1.hosting.example.net? RFC 7673 specifies that the TLSA record should be looked up at the target server hostname that the SRV record points to. This makes sense because the target server is what actually presents the TLS certificate. The service domain owner delegates to the hosting provider by publishing the SRV record, and the hosting provider publishes the TLSA record for their server. However, there is a security consideration. The SRV lookup must also be DNSSEC validated. If an attacker can forge the SRV record, they can redirect the connection to their own server with their own matching TLSA record. The entire chain from the original service domain through the SRV record to the TLSA record must be secured. The diagram illustrates this flow, showing how the client follows the SRV indirection and then looks up the TLSA record at the target host name. Deployment Best Practices Summary. Based on everything we have covered about RFC 6698 and its related specifications, let me summarize the key best practices for deploying DANE TLSA successfully. First and most importantly, ensure your domain has properly configured domain name system security extensions before publishing any transport layer security authentication records. Test your domain name system security extensions deployment thoroughly. A broken domain name system security extensions configuration will cause data availability and name entity aware clients to reject your service entirely. For most deployments, use certificate usage 3, which is DANE-EE, with selector 1 for subject public key info and matching type 1 for SHA-256. This combination provides strong security while allowing certificates to be renewed without updating TLSA records, as long as the same key pair is used. Plan your certificate rollovers carefully. Add the new TLSA record before changing certificates. Wait for the old record's TTL to expire, then switch certificates, and finally remove the old TLSA record. Never skip the waiting period. Set appropriate time to live values for your TLSA records. Shorter time to lives allow faster recovery from misconfigurations, but increase DNS query load. Longer time to lives reduce load, but require longer rollover windows. A time to live of 1 to 4 hours is common for production deployments. Monitor your DANE deployment continuously. Use online DANE checking tools to verify your TLSA records are correctly published and match your certificates. Set up alerts for DNSSEC signature expiration. Consider the client ecosystem. While DANE support is growing, not all clients support it yet. Ensure your service works correctly for both DANE-aware and traditional clients during the transition period. The checklist on the slide summarizes these practices for quick reference during deployment. Conclusion and key takeaways. We have now completed our comprehensive exploration of RFC 6698, the DNS-based authentication of named entities TLSA protocol. Let me summarize the key takeaways that you should remember from this presentation. DANE TLSA solves a fundamental problem with the public certificate authority model by allowing domain administrators to specify exactly which certificates are authorized for their TLS services. This shifts trust from a large set of unrelated certificate authorities to the DNS hierarchy itself, where each domain controls only its own assertions. The TLSA record structure provides flexibility through its 4 fields. Certificate usages 0 through 3 support different trust models from certificate authority constraints to fully domain-issued certificates. Selectors allow matching against full certificates or just public keys. Matching types support exact comparison or cryptographic hashes. DNSSEC is absolutely essential for DANE security. Without DNSSEC validation, TLSA records provide no security benefit. Implementations must verify DNSSEC signatures and must abort connections when validation fails. Operational procedures like certificate rollover require careful attention to DNS TTL values and proper sequencing of record updates and certificate changes. The pre-publish method prevents service disruptions during transitions. The DANE ecosystem continues to grow with related standards for SMTP, SRV records, and operational guidance. Adoption is increasing, particularly for email security where DANE provides significant benefits. Thank you for your attendance. Please consider subscribing to the channel and liking this video.